definitions, and then we can play with some stuff. If I use the notation A minus B, where A and B are sets, that means the set of X that is in A and X is not in B. So basically you're tossing out anything that's B related from A. So for example, if A was equal to 1, 2, 3, and B was equal to, ooh, that's spastic, 3, 4, 5, then A minus B means we start with A, and anything that is in B that's also in A gets tossed out. So all we toss out is the 3. So A minus B is the set 1, 2. Another way of looking at A minus B would be A intersection B complement. Just another way of thinking of it. The other definition, a little bit bigger one, is for cross product or just plain product. So assume A and B are sets. Duh. A cross B, which is red, A cross B is the set of ordered pairs little a comma little b, where little a is in big A and little b is in big B. Think about it as we have the reals cross the reals is the real plane. So that's kind of our first set that we've ever crossed. But let's look at some smaller sets so we can get a feel for what's going on here. But I don't want to go crazy. Let A equal 1, 2, 3, because I have no imagination, and B equal X, Y, Z. Kind of want them to be different so I can show the cross product better. If I have A cross B, well, that means I have order pairs with A's in the fronts and B in the second. So we're going to have 3 from A for each 3 in B. So we're going to have 9 possibilities. So the order of A cross B in this case is 9. Oops, went off the page. And in general, the order of A cross B will equal the order of A times the order of B. Okay, so A cross B, I have to do 9 of these things. I have 1 comma X, 1 comma Y, 1 comma Z. Ding, like a typewriter. 2 comma, like you know what a typewriter is. 2 comma X, comma, 2 comma Y, comma, 2 comma Z. Then I have 3 comma X, 3 comma Y, 3 comma Z. No, you don't have to write them in rows, but it was easier to see it that way, and there's no room to go over here, so that's what I did. So let's talk about some theorems that you might have for these cross products. Do this. Theorem. Everybody's a set. A, B, C, and D are all sets. A cross B union C is equal to A cross B union A cross C. Proof. Now, to show two sets are equal, I need to show that they're subsets of each other. I'm going to start on the left, let something be in here, blah, 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 and show that it's on the other side. Now, anything in here is an ordered pair, so I'm going to write it like that to make my life a little bit easier. So anything in here is of the form, let's see, let X comma Y be an element of A cross B union C. Now, if that's true, that implies that X is in A and Y is in B union C. That implies, well, if X is in A, I'm leaving that one. If Y is in B union C, that means Y is in B or Y is in C. Now, we know from logic that AND distributes over OR. So that means X is an element of A and Y is an element of B, or X is an element of A and Y is an element of C. Now, bringing this back together so I get back to this cross notation. If X is in A and Y is in B, that means the ordered pair XY is in A cross B. Or, if X is in A and Y is in C, that means X comma Y is an element of A cross C. Well, if X is in A cross B, if XY is in A cross B, or it's in A cross C, so think about this, I've got an element in one set or the same element in another set. That means it must be in the union. So I started with something on the left and ended up with something on the right. So officially, right now, I've shown that A cross B union C is a subset of A cross B union A cross C. And I need to go the other way to prove the other subset. Now let's think about this though. XY, an element of A cross B union C, is by definition means X is in A and Y is in B union C. And when you have definition, that means if and only if. So I can make that an if and only if. To say Y is in B union C implies Y is in B or Y is in C. That's also by definition. So that's if and only if. All of these steps were if and only if. So because we are able to do the same thing forwards and backwards, if and only if, we are actually done. And we can say that A cross B union C is equal to A cross B union A cross C. There are other theorems, as you might imagine. We can say that A cross B intersection C is A cross B intersection A cross C. We can say that A cross the empty set is the empty set. We can say, oh, this one's a gross one to prove, so I'll let you do it in class. A cross B intersection C cross D is equal to A intersection C cross B intersection D. Yeah. What about union? A cross B union C cross D is equal to, no, it's not. It's not equal to. It's actually a subset of. It's equal to, sorry, it's a subset of A union C cross B union D. The key is, on this side, I can get something from A cross with something from D. Whereas that's not going to happen over here. All the A's are with B's, all the C's are with D's. So that's why this is actually a subset. When we did the intersection, we took care of that case. And what's that? Oh, it's the same theorem. So those are the theorems I'm going to want to look at in class. And we can prove some of them. But I want to start playing with some of these cross products because we're going to have to be using some of them with the extended sets. That's a horrible way to end the video, but that's the way I'm going to end it. Good night.